Hello everyone. Let's look at some examples involving application of KVL and KCL. While solving these circuits, I want you to keep one thing in mind. You have to be ruthless in your insistence of following definitions and physical laws. That means no hand waving. Any statement you make must be backed either by a definition or by physical law. If it's not, then you cannot make that statement. Let's look at assessment problem 2.9. Okay, as you can see, there are three independent voltage sources here, and there is one dependent current source where the current in the source is dependent on this current here. The first problem is asking us to find I1 in microamperes. Okay, so first thing I want to do is label the current here as I. All right, and then I can do a KCL at that node. The statement for KCL is sum of all currents going into a node is 0. So if I apply KCL at that node, I'm going to redraw that node at the bottom just for convenience. Here is the part of the circuit I'm concerned with. So, and this is the node I want to draw. I want to write the KCL equation at. Now, if I sum all the currents going in, so starting from left hand side and going anti-clockwise, current going in is I1. On the bottom, the current going in is minus I. On the right, the current going in is plus 30 I1. This should be equal to 0. This implies I should be equal to 31 I1. The next thing I want to do is write a KVL equation in this loop here going clockwise, starting at that point and coming back at that point. I'm going to redraw that part of the circuit again for convenience. Here's the circuit, I'm redrawing it. So I'm going to write the KVL equation on this loop. And remember, this is not the entire circuit. The statement for KVL is sum of all voltage drops is equal to 0. So in this case, then that would be going clockwise. First, I have a voltage increase of minus 5 volts. Plus, I have voltage drop of 54 times I1. Note that I'm using kilo ohm as the base unit for resistance, volts as the base unit for voltage. That means the base unit for current is automatically milliamps. There is another voltage increase of 1. There's another voltage drop of 6 times I, and this should be equal to 0. I'm going to simplify this equation here. So this should be equal to 54 I1 plus 6 times 31 I1, because I is equal to 31 I1, and this should be equal to 6 volts. Factoring out I1, I get this equation. Multiplying 6 times 31, I get this. Further simplification, and I finally get I is equal to 6, I1 is equal to 6 over 240 milliamps. Note that I'm using milliamps because that was my base unit, which I selected before. That will give me I1 as 0.025 milliamps, which will be equal to 25 microamps. Okay, and then the question asks me to express I1 in terms of microamps. That's why I have this. Part B asks me to calculate the voltage. I will draw the relevant part of the circuit here. So this is the second loop in the circuit which I can use to calculate V. So what I'm going to do is I'm going to apply KVL in this loop, starting at this point, ending at that point again in clockwise direction. So first going up, there is a voltage drop of 6 times I from top to bottom. So there is a voltage increase of 6 times I from bottom to top. Plus there is a voltage drop of V. Plus there is an increase of 1.8 times 30 I1 across the 1.8K resistor. plus there is a drop of 8, that should be equal to 0. Rearranging the terms and substituting I for 31I1, I get this equation. I factored out I1. After addition, I get this, and then I get this, and this should be equal to negative 2 volts. That should be equal to V. Then they're asking for the total power generated. Just as a refresher, if power associated with a component is negative, then that implies power is being generated. In the given circuit, we have some resistors, and we know resistors cannot generate power, so we only have to look at the sources. We have 4 sources here, and we will look at the power associated with each of those sources and see if they're positive or negative. Let's look at the 5 volts voltage source, and I'm just going to draw the relevant part of the circuit again for convenience. So here's the 5 volts source, and there's a current of I1 going from bottom to top. Okay, that means the power associated will be equal to 5 volts times minus I1, because minus I1 is the current in the direction of the voltage drop. This will be equal to negative 5 times 25 microwatts. Then this will be equal to minus 125 microwatts. So since this is negative, that means this 5 volts voltage source is generating power. Let's look at the 1 volt source. Here's the relevant part of the circuit. The power associated will be voltage drop of 1 volt times the current in the direction of the voltage drop is negative I1. Substituting the values for I1, I get the power associated is negative 25 microwatts. Since the power associated is negative, this is also generating power. Let's look at the controlled current source. Here is the relevant part of the circuit. Power associated would be the voltage drop V times the current in the direction of the voltage drop, which will be equal to minus 30 I1. Substituting the values for V and I1, we get a positive value. So this current source, controlled current source, is not generating power, but it is absorbing power. Let's look at the 8 volt voltage source. Power associated would be the voltage value times the current in the direction of the voltage drop, which will be equal to negative 30 I1. Substituting the value for I1, we get negative 6000 microwatts. Since the power associated is negative, this is also generating power. The total power generated would therefore be equal to 125 microwatts. This will be by the 5 volt voltage source plus 25 microwatt. This will be by the 1 volt voltage source plus 6000 microwatt. That will be by the 8 volt voltage source. And the total comes out to be 6150 microwatt. This will be the total power generated. Part D asks for the total power being absorbed, which will be equal to the total power generated, which will be equal to 6150 microwatts. Let us look at another example. In this example, we have one independent voltage source, one independent current source, and another dependent current source. The current in the dependent current source or the controlled current source is given as 2 I phi, where I phi is the current going through this resistance here. It is also given that I phi is 2 amps. Part A is asking us to find the value of Vs. Let us assume that the current through this branch here is I. Then I can write a KCL equation at this node here. I'm going to redraw that part again in the bottom for convenience. Here is the redrawn circuit with the node where we want to write the KCL equation. The KCL equation would then correspond to the statement, the sum of all currents going into that node should be 0. Current going into the node from the left hand side is 5. In the bottom, minus I phi. On the right hand side, plus I. And on the top, minus 2 I phi. This should be equal to 0. Rearranging things, I should get I is equal to 3 times I phi minus 5. And it is given that I phi is 2 amps. This will give me I is equal to 1 amp. Now that we know I is equal to 1 amp, we can write a KVL equation in this loop here and then find out what Vs is. Again, I'm going to redraw the circuit for convenience. So this is the loop where we want to write our KVL equation. Remember that this is only a part of the circuit. So the KVL equation, starting at this point here and going clockwise direction. First, we have a voltage increase that would be minus 30 times 2. So that's how much you have a voltage increase going up. On the 10 ohm, we have another voltage increase of 10 times 1. And then there is a voltage drop of Vs, and that will be equal to 0. Right, so we have the KVL equation as the sum of all voltage drops is equal to 0 along the loop. Rearranging, I have Vs is equal to 70 volts. Part B is asking for the power absorbed by the independent voltage source. Note that the question itself is telling us, is giving us a hint that the power associated with the independent voltage source should be positive because they're asking for power absorbed by it. I'm going to redraw the part with the independent voltage source to make for our convenience. So here is the part of the circuit with the independent voltage source. What we need to find is the current in the direction of the voltage drop. Let's call this I1. Then writing a KCL at that node, we get 2 I phi minus 1 minus I1 should be equal to 0. This implies I1 will be equal to 2 I phi minus 1. So this would be 4 minus 1 is equal to 3 amps. And we already know Vs is equal to 70 volts. The power associated will then be the voltage drop Vs times the current in the direction of the voltage drop, which is equal to I1, which in this case is 70 volts times I1 is 3 amps, and then you get 210 watts. Part C is asking us for the power delivered by the independent current source. Again, it is hinting that the power associated would be negative. Here is a part of the circuit involving the 5 amp independent current source. In order to find the power associated, we need to find the voltage drop across it, and we can do that by looking at the 30 ohm resistance. So V will be equal to, in this case, 30 ohms times 2 amps, and that would be equal to 60 volts. The power associated would then be equal to the voltage drop, which is V, times the current in the direction of the voltage drop, which is minus 5. Substituting the values, I get the power associated as negative 300 watts. Since the power associated is negative, then the power is being developed in this source. which tells us that the power delivered is equal to 300 watts. Part D is asking us for the power delivered by the controlled current source. Here is a part of the circuit corresponding to the controlled current source. In order to find the power associated with it, we need to find the voltage drop across it, which we can find using the 10 ohm resistance. So we have V in this case will be equal to 10 times 1, which will be equal to 10 volts. The power associated will then be equal to the voltage drop V times the current in the direction of the voltage drop, which will be equal to minus 4 amps. Substituting the values, we get the answer as minus 40 watts. Since the power associated is negative, that means the current source is developing power or delivering power, and that power delivered will be equal to 40 watts. Part E is asking for the total power dissipated in the two resistors. We will use the fact that the total power is conserved, and therefore the total power developed should be equal to the total power absorbed. Both the independent current source and the controlled current source are delivering power, and the power they're delivering or developing is 300 watts plus 40 watts, which is a total of 340 watts. And we also know that the voltage source, independent voltage source, is absorbing power, and it is absorbing 210 watts. So the 210 watts, in addition to the power absorbed by the resistors, should be equal to 340 watts, which implies the power absorbed by the resistors is equal to 340 watts minus 210 watts will be equal to 130 watts.